Okay, I will start now.
Sure.
Hello, everyone. My name is Ajay Jacob. I am the Director of Projects at the California Dreams Hub. It's my pleasure to invite Professor Susumu Takahashi from USC. He is a professor of physics and also chemistry and astronomy at the University of Southern California. He was a visiting professor at Institute for Solid State Physics at University of Tokyo. He previously worked at UCSB as a postdoc, and also he did his PhD from University of Florida. So it's my pleasure to invite Professor Takahashi to give a talk on solid-state qubits for quantum sensing and communication. The stage is yours, Professor Takahashi.
Thank you, AJ. All right, so I wanna today talk about the solid-state quantum systems, and particularly for quantum sensing and also communication applications. So we are interested in quantum mechanical properties of the solid-state spin systems and also different other type of the qubit systems. So because of the, so first of all, quantum mechanical properties is very interesting fundamentally because we can see a very unique phenomena, which is different from our intuitions based on the classical physics. But also use of the quantum property is a promising way to improve the technologies. And then particularly, so use of the quantum property for the sensings and the communications and the computing is very promising directions. And then this can be a next generation technologies. So I'm going to show you some examples. So for instance, quantum sensing is the technique can measure the physical properties. And then particularly using the quantum mechanical property, we can improve the sensitivities and also, for instance, spatial resolution of the images. So here I show you the example of the imagings of the fluorescence, and particularly using the quantum mechanical properties. This example shows that we can improve the spatial resolutions. So this is a fluorescence image coming from so-called single photon emitters. So within this emitters, within this image, there are actually two quantum mechanical emitters. And then if we measure the just intensity of the light, then the image will be as shown on the left side. So as you can see, there are actually two emitters, but we cannot distinguish those emitters because of the diffraction limit of the photons. And then, but if we use the quantum mechanical detections, so the quantum emit the photons, and each photon is quantum mechanically correlated. And if we measure those correlations of the photons, so we can improve the spatial resolution of the imagings. So on the right side image shows the example of the quantum, the measurement based on the quantum correlations. So you can clearly see the two photon emitters, and then the resolutions of the image is beyond the diffraction limit. So this is one of the good example of the quantum sensings, which can improve the resolutions beyond the classical limit. And then, yeah, this demonstration was done by the Dan Oron group in the Weizmann Institute. And also, we can use the quantum mechanical states to improve the sensitivity and the resolutions. And this can be superposition states for the single qubit systems. And also, we can use the entangled states, which is made out of the multiple qubit systems. And then those coherent states can be used to improve the sensitivity in a quantum sensings. So quantum sensing is as I said, is promising to the applications. And then since the quantum sensing uses the same principle of the quantum computers, but for instance, the states we use for the sensing is much simpler than the computing. So people think that quantum sensing can be commercialized earlier than the quantum computing. So not just only scientists, many people interested in the quantum sensing itself. And then this report came from the consulting companies. So as you can see, so these companies interested in the application of quantum sensing and then commercializing the quantum sensing device for these applications. So in my lab at the USC, we are interested in several directions of the research. So one of the direction is that quantum sensing, particularly we want to improve the sensitivity of the magnetic resonance techniques, such as electron paramagnetic resonance or nuclear magnetic resonance. And then this case is using the NV centers in the diamond. And particularly, we want to apply this NV detected magnetic resonance techniques to the high magnetic field for applications in chemistry, biology, and physics. And we're also interested in to study different type of the qubit systems in solid state, states and also molecular systems. So we're interested in the defect spins in wide bandgap semiconductors, and also molecular spins, and also the spins in the two-dimensional materials, and also ensemble spin systems. And also the other interest is we're interested in quantum dynamics itself, including the entanglement and also spin squeezing. We recently published the papers to propose the experimental demonstration of the spin squeezing, which can be useful to improve the sensitivity of the quantum sensings. And also as an interest is we are interested in, to control the electronic states of the qubit by using the electric field. So in this project, we use the high electric field or high voltage pulse to control the electronic the properties of the qubit. So in this talk, I want to talk about the our project of the quantum sensings for the magnetic resonance, and then also the electrical control of the qubits. So these projects, both of them are supported by National Science Foundations. For the quantum NV detected magnetic resonance has been supported by NSF for a while. And then also this electrical control of the charge states or electronic structures. Also, this is a collaborative project with the Steve Cronin group at the USC. So this is also supported by National Science Foundations. So I'd like to start with the NV centers in the diamond. So this is the key quantum sensors used in this project. So NV center in a diamond is made out of the substitutional nitrogen in a diamond lattice next to the vacancy. So it's a missing carbons. Then this has it's a negatively charged, actually, the negatively charged defect, which has 6 electrons in the systems. And then because of the triplet configurations, so the ground state is triplet states. So this also NV center has excited states, which we can access to the lasers. Then that's also triplet states. Then there is the intermediate singlet states. So in the experiment, we can use that the laser excitation and fluorescence imaging. So this graph shows the fluorescence imaging of the diamond, and then some of the darker spots is, so this shows the NV center in the diamond, near the diamond surface. Then particularly, so in this optical excitations, we excite the ground state electron into the excited state. And then this is the spin conserving excitations. So this 0 states goes to 0, and the plus minus 1 goes to plus minus 1 states. Then 0 states gives us the strong fluorescent signals. So by looking at these fluorescent signals, by measuring the fluorescent signals, so we can measure that correlation of the photons. So, and then particularly in experiment, we use the so-called G2 measurement. And then this G2 functions physically means that probability to find the two photons simultaneously, particularly at when the tau equals 0. So as you can see, when the tau equals 0, so G2 functions goes to 0. So that means that the signals and at the this image is showing that coming from the single photon source. Okay. So and then, so this is that how we can actually detect the single photon emitters. So in addition, there's optical excitations, and particularly optical relaxation is very actually unique in this NV centers. So for MS equals 0 states, so the most of the excited electrons going back to ground states directly. And on the other hand, in the case of plus minus 1 state, there are two possibilities. So this can go back to ground state directly, but also there is almost same probability going to intermediate states. So because of this difference, so the fluorescence intensity for the 0 states and then plus minus 1 state is different. For 0 state, we have a brighter fluorescence than the plus minus 1 state. So by using this difference, we can read out the spin states. So when the spin state is in 0, we can have a higher intensity of the photons. And then when the spin state is plus minus 1, we have a lower intensity. So in addition, so once it goes to intermediate states, eventually mostly going back to 0 state. So just by shining the lasers, we can make this optical cycle many times. And eventually all the spin, all the electron is coming back to this 0 state. So by using this, the optical excitations, we can initialize that NV spin states into MS equals 0 states. So we can have about 70% of the polarizations. So, and finally, if we apply the microwave to excite the spin transitions, so we can manipulate those spin transitions coherently. So then we can read out through the fluorescence. So we can perform the magnetic resonance of the NV centers at the single NV center levels. So this technique for magnetic resonance using the microwave the manipulations and the optical detection is so-called optically detected magnetic resonance, ODMR. Using the ODMR, we can detect the single NV centers and then study the single NV center. So then also the spin states of the NV centers, so depends on many environment. So here I show the spin Hamiltonian of the NV centers. So NV center spin Hamiltonian is depends on magnetic field, which is coming from this Zeeman term. It also depends on the temperatures. So this D term in Hamiltonians has a strong temperature dependence. And also the constant in this terms has an electric field dependence. So we can use the NV center to measure the magnetic field and also to sense the temperature and the electric field. So we can see an NV center in a single spin level, which is atomic size, to measure the magnetic field and also temperature and the electric field. So this NV center, particularly for magnetic field, we note that this is very sensitive to the magnetic field. So this graph shows that, so the x-axis shows the magnetic field sensitivity. And then y-axis shows the separation, it's a distance from the NV center sensor to the sample spins. So, and then as you can see, so this line represents that this is the sensitivity required to measure the single electron spins. Actually, so this blue lines represent the required sensitivity to detect a single electron spins. And then single nuclear spins, single proton spins can be detected if we have a sensitivity of these lines. So experimentally, we can achieve the sensitivity of this range. So it's about 10 to minus 6 Tesla per square hertz. So then we can, since the NV is a very small sensors, so we can place the NV in a distance of the tens of the nanometers. So NV center is definitely sensitive enough to measure the single electron spins. And then if we do it correctly by having the right sample configurations, it may be possible to measure single nuclear spins, or at least thousands or hundreds of the nuclear spins. So using the NV, there are many beautiful demonstrations has been done. So for instance, the Amir Yacobi group at the Harvard University built the scanning probe systems based on the NV center in a diamond. And then they measure the magnetic profiles of the scumion, the materials. And then so this is the magnetic image taken by them, and showing that the new scumion patterns from the samples. And in addition, this is another demonstrations done by the Dominic Bouchard group in Germany. So they demonstrated that using this NV center in a diamond near the surface of the diamond, so they can measure the NMR signals, and then particularly in these demonstrations, they measure the fluorine NMR signals, so F19 NMR signals, while they are placing these molecules, so ETOH molecules on that near the diamond surface, and then they monitor that how that this assembly of the molecules is done. And so during the self-assembly process was monitored by using the NV probes. All right, so in addition, so we do use that NV centers to the magnetic resonance, and I want to explain the one techniques to measure the magnetic resonance by using the NV centers. So there are several ways, but I think the method we often use involves this double resonance techniques. So particularly, I explain these techniques based on the electron spin detections, but same technique can be applied to measure to detect the nuclear spins. So we have this quantum sensor NVs as shown in these pictures. In addition, we have a target spins. Then for NV, so we make the coherent states. So in this example, we make the superposition states by using the single NV centers. Then by using this technique, pulse sequence, so-called a spin echo sequence, so we keep the spin echo, we keep the coherent states by using the spin echo sequence. So in this example, we made the initial state of the minus X states, and we keep these states along the X directions. So at this timing, so we made the states along the X states. So in addition, so we apply additional pulse to flip this target spins. So by flipping this target spins, now this NV center experiences a definite magnetic field because the target spin is principally a tiny magnet. So by flipping the spin, so now magnetic field at the NV center is different. So this will change the precession frequency, normal frequency of the NVs. then at the same timing tau, so the state is different. So it's shifted from the x-axis. And then by using the measurement, quantum mechanical measurement, so we can measure the shift of the states from the state measurement. All right. So in experiment, so that's in experiment is actually, so we in experiment, so we change the frequency of the second pulse to flip the target spins. So when it's coming from the off resonance, so nothing happens. And when it's coming to on resonance, we see a smaller probability to find original states. And then going back to off resonance, we have a higher probability to find original states. So by measuring the spectrum like this, that gives us that. So this is a magnetic resonance of the target spins. And the sensitivity of the technique depends on how long we can keep the coherent states. So the principally coherence time of the NBs determine the sensitivities. So in the case of the NB centers, so for instance, if we have a T2 of the 100 microsecond, so which can be, which is possible even at the room temperatures. So we can measure the single electron spin, which is 25 nanometer per of the NBs. So this is actually a very long distance in the molecular scale. So the NB center can actually measure the single electron spins located far from, it's more than size of the molecules. All right, so then, so we want to actually use those NB centers to perform, to improve the sensitivity of the EPR and NMRs. And then in my lab, particularly focus on at the high magnetic field. And then because in the magnetic resonance, usually often gains that we have lots of advantage going to the high magnetic field. So for instance, in the conventional NMR machines, will be available around 80 megahertz, and then which is actually regularly used to actually characterize the molecules. In research lab levels, for instance, in a chemistry department, have the 9.4 Tesla NMR systems, which corresponding to proton Raman frequency of the 400 megahertz. So this is also available in many universities, and then also the many in the national labs developed even higher magnetic field NMR systems. So, and then these going to higher frequency, higher magnetic field actually gain NMRs to improve the sensitivity of the NMR. Also, this improve the spectral resolutions, which can be more, the high field NMR can be more sensitive to measure the small difference of the chemical shift. So it's very useful to go to higher magnetic field. And then on the other hand, many NB NMR experiment has been done actually low magnetic field so far. So many of the study has been done less than 0.1 Tesla. And then there are some demonstrations done by 3 Tesla. So this was done by a Raptor group at the University of Stuttgart in Germany. And my lab has been developing the NB detected NMR and EPR systems, even higher magnetic field. We've been doing this more than 10 years. So we have demonstrated ESR measurement at the 4 Tesla, and then we have demonstrated NB NMR measurement at the 8 Tesla. So then for us, so doing the NB detected NMR at the high magnetic field is, first of all, we can improve the spectral resolutions of the signals. And then also the high field can be advantage to detect the many nuclei. So there are many nuclei has a smaller gyromagnetic ratios, very difficult to detect at the low magnetic field. And then also for the NMR measurement, some NMR measurement based on NVs, we can improve the sensitivities. So we are interested in developing the high field NMR, NV detected NMR techniques. And one of the applications we think is interesting to do that at the high magnetic field is to study a surface, some surface chemical reactions. So for instance, application to the heterogeneous the catalyst. And then we want to study those chemical reactions by using the NV detected surface NMR techniques. So this is example. So here, now I'm going to show you what we're doing in my research lab. So this is, so first of all, start from how we're gonna develop the systems. So our systems is use that high magnetic field and then also high frequency microwaves. So for the magnet, we use the 12.1 Tesla sweepable superconducting magnet. Then in addition, so we combine the high frequency microwave systems into this high field magnet, superconducting magnet. So our frequency range is 107 to 120 gigahertz and also around 230 gigahertz. And then this is a source of the microwave. So it's based on the low frequency 10 gigahertz microwaves. And then using that frequency multipliers, we increase the frequency of the microwaves. So up to 115 or 230 gigahertz. So, and then we have a two microwave source. This is for the NV detected ESR measurement. So one for NV and another one for target electron spins. So for these microwave frequencies, it's very high frequency. So wavelength is about millimeters. So it's more efficient to actually propagate into the free space than using the waveguide. So we built those microwave propagating systems based on the so-called quasi optics. So this is based on the Gaussian optics of the 100 gigahertz of the microwave. And then so propagate into free space and coupled to the waveguide, and then eventually coupled to the sample, which is located at the center of the magnet. And then also we have this microwave detection system. So this is for conventional ESR or EPR measurement. So in addition to the ODMR, we can perform the EPR, which is convenient to test the sample. So then also for the ODMR detections, so we have the laser access and the fluorescence detection paths coming from the bottom of the magnet. So we use the solid state lasers and AOM, and then we have the steering mirror for the imaging of the diamond, then using the lens and also objective. So the laser is focused down to the diamond surface, and the fluorescence is detected by the same objective, and then going to the detectors, which is based on the avalanche photodiode. So, and recently we added some capability to shape the microwave pulse to improve the fidelity of the ODMR techniques. So we have demonstrated, so this is the ESR detections based by the NVs. So this case, this signal is coming from the single NV sensors and then performed at the 4.1 Tesla. So, and we can clearly see nitrogen. So this is the P1 center signals. And then this is another experiment of the NV detected ESR techniques. So in this case, so we could measure the isolated nitrogen spins in the diamond, and also we see some broad ESR lines. in this particular locations. So, and then later we found out that so these actually broad line is coming from the clustered the nitrogen spins. So by using the high field techniques, actually is helpful here. In addition to see isolated spins, and also we could observe the clustered the spins. So this is because of the higher spectral resolution. So in addition, so we can perform the NMR at the 4 Tesla and 8 Tesla. So this is a demonstrations to measure the carbon-13 NMR signals. And then in this particular demonstrations, so we improve the spectral resolutions of the carbon-13 NMR signals down to the level of the tens of ppms. So, and then in this particular demonstrations, we are detecting about the 10 to the power 8 nuclear spins. So we use those NV detected NMR techniques to study. So for instance, we can use those techniques to, for instance, to study heterogeneity in nanometer scales. So in this demonstrations, so we looked at the many different locations of the diamond. And then, so each measurement, so we measure the concentrations of the spins at each locations. And then it's actually well known that so concentration of the paramagnetic spins is important parameters to determine the T2. So we looked at the different locations of the diamond and measure the T2 and also the concentrations. Then we measured by measuring those. So we study the relationship between the spin concentrations and the T2s. So, and then theoretically it's expected to have a linear dependence. And we found out that so linear dependence is very good linear dependence in the low concentrations of the spins. But when it's going to higher concentrations, there are some deviations, so which may coming from the effect of the clustering and so on. So by using this NV detected ESR techniques, we can measure the so local properties or local environment of the samples. So another demonstrations I want to show here is that so using the NV, so we detected only 2 nearby spins. So in this experiment, so we looked at the single NVs, and then we measure the double by using the double resonance technique, and then we measure that spectrum coming from the ESR spectrum detected by NV centers. And then by analyzing the spectrum, so we found out that so this NV coupled to 2 electron spins, and then these are coming from which made these oscillations. And analyzing these oscillations, we can determine how many spins coupled to these NV centers, and also strengths of the interactions. So by using this NV centers, so we can measure the nearby spins. In addition, we can characterize the strengths of the interactions. So which is important parameters. Actually, strength of the interaction is important parameter to make the network of the interacting spins, particularly to make the entangled state. So here is the part of the magnetic resonance using the NVs. So using the NV center in a diamond, so we show that we can perform the EPR and NMR, particularly at the high magnetic field. And then also this method can detect the, this method can improve the sensitivity of the magnetic resonance techniques. And then we are interested in to apply those techniques to study surface chemical reactions by using surface NMR technique. And then also another interest is that we want to, so we recently started thinking about how we can improve the sensitivities, and the quantum mechanics can be, quantum dynamics can be an interesting way to improve the sensitivity. So recently, we investigated that so-called squeezing. So the squeezing is that so it's a state we can reduce the uncertainty of the physical quantities. So as you may know, that this Heisenberg uncertainty relationship states that when physical quantity A and B, physical observable A and B doesn't commute, and then we cannot determine observable A and B simultaneously. And then there is an uncertainty of the physical observable A and B's. And for many states or usual states, this uncertainty is same. So it makes the isotropic uncertainty shape. But by choosing special states, so-called squeeze states, so we can make the one of the uncertainty smaller and the other one is larger. So principally using the squeeze states, we can reduce the amount of the noise in the quantum measurement, and then so that we can improve the sensitivity. So the spin operators like Sx and Sy also don't commute. So we can apply the same principles. So then by using the spin squeeze state, which is special spin states, so we can reduce that the uncertainty of the Sx or Sy, and then use those smaller uncertainties of the more sensitive measurement. And then it's known that this ingredient to make such a state is interaction between spins. So interacting spin states is important. So our recent studies, so we looked at the dipole interacting spin systems, and then we found that using those dipole interactions, we can make the squeeze states. And then we described how to realize those squeeze states by using that. So this experimental realizable pulse. So we also found out those squeeze states is part of the entangled states. So by observing the squeeze states can be the method to detect the entanglement in the systems. So we are interested in use the squeeze states for the quantum sensing, and then to improve the sensitivity and also to detect the entanglement in interacting spin systems. So so this is the first part of the project. And then next I want to talk about the electrical control of the charge states, the electronic states of the NV center, and then silicon-vacancy centers in the diamond. So this is a collaborative project with the Steve Cronin group at the USC Electrical Engineering Department, and then supported by NSF. So NV center in a diamond, the sensor we use is negatively charged NV centers. So this is the electronic structure of the NV centers. So it has 4 orbitals. So it's originated from the sp3 orbitals in the diamond. And then because of the broken symmetry, so the degenerate sp3 orbitals, degeneracy in sp3 orbitals is lifted into this weight. And then we have 6 electrons in the systems. Then it makes the triplet states. So this is ODM active, as I explained previously. And also there is the neutral charge states. If we take out the 1 electrons, so we have only 1 unpaired electrons. So this is spin half systems. There is no ODMR. And then we can also take out the 2 electrons from the NV minus. So this becomes the positively charged NV centers. Then now this NV doesn't have an unpaired electron, so S equals 0. So these different charge states can exist within a diamond. And then this DFT calculation study shows that, so this is the charge states or possible charge states of the NV centers. And then these charge states are energetically favorable and depends on the Fermi energy of the diamond. So this lower line is the valence band of the diamond, and the upper line is the conduction band of the diamond. So if we have no doping, the Fermi energy is almost in the middle. So it's a boundary between minus and zero states. And if we dope that the donors, Fermi energy is going up. So minus state will be energetically favorable. But if we dope the holes, then zero state is more energetically favorable. So the Fermi energy is very important to have, for instance, NV minus states. And then also we got interested in another defect center in a diamond. So here is a so-called silicon-vacancy center in a diamond. So this is another defect in a diamond is made out of the interstitial silicons next to the vacancies. So this silicon-vacancy center is very interesting because of has a very narrow emission lines. So this graph shows the fluorescence spectrum of the NV minus center in a diamond, which has about more than 100 nanometer wide. But on the other hand, the SIB minus centers has a very narrow emission lines. Almost there is no side band. So this makes that emission line is very narrow. So in addition, so this silicon SIB minus has the spins, and then ODMR has been demonstrated in the systems. So not surprisingly, SIB also has multiple charge states. So this can be neutrally charged, and then also this can be doubly negatively charged states. And then, so this SIB minus and SIB zero. So both of them ODM are active, and then it has a spins. So SIB minus is well studied. And then we note that the coherence time of the SIB minus is very actually short because of the strong spin orbit couplings. And in order to minimize the effect of the spin orbit coupling to have the longer coherence times, so we need to go very low temperatures, tens of millikelvins by using dilation fridge. On the other hand, so this SIB zero state has much longer coherence time, even at the higher temperature. So this is because of the it has the smaller spin orbit couplings. So the T2 is not affected by, looks like it's not affected by spin orbit couplings. So potentially this SIB zero is potentially is more interesting for the sensing and also the quantum communications applications. So this is the spectrum of the SIB zero centers. So it's about 946 nanometers. But this SIB zero is not well studied. This is because that, so again, so this is the charge states, energy diagrams. This is the conduction band, and then this is the valence band. And then in order to realize the SIB zeros, we need to lower the Fermi energy a lot. And by doping the acceptors, and so we need to have a very it's a heavy material science to realize such charge states. So, but we recently found out that by using this electric field, so this is the high voltage pulse can modulate, can change the charge states effectively. So this is our experimental setup. So we have the diamond substrate. So in this experiment, in this particular experiment, diamond contains the SIB and NV together. And then we measure the fluorescence of this diamond by using the 532 excitation laser. and then detected by spectrometers. And then diamond has an electrode on the top surface and the back surface. Then from the back surface, we apply the high voltage pulse, which is about 20 nanosecond duration. And then, so originally experiment was first done by the Steve Cronin groups, and then they observed this spectrum. So when it's high voltage pulse is not applied, so they only observed NV spectrums. And then when the high voltage pulse is applied, they started to see SIB spectrums over here. And then by changing the frequency of the high voltage pulse, so this is the repetition rate of the high voltage pulse, from 0 to, so please by 1,000 hertz, so 1,000 high voltage pulse per second. And then they observed the strong, the increase of the SIB signals. And then they also observed the broadening of the NV spectrums. So then when we looked at the this spectrums, and then I thought it's interesting to actually analyze the NV spectrums. So in the original papers, they studied how the SIB spectrum is increased. And then this NV spectrum was not analyzed well. So I thought it's interesting to analyze NV spectrums. And particularly, so since I knew that this NV spectrum can contain both spectrum of the both charge states of the NV minus and NV zero. So this graph shows that how we can understand the NV spectrums. So NV spectrum is made up of the combination of the, so this is the NV minus spectrum, and then this green one is NV zero spectrums. So label is actually wrong. So green one is NV zero, and then pink one is NV minus. And then so total spectrum is made out of the combination of those two. So by decomposing this total spectrums, so, and then by using this, the minus and zero spectrum, now we can actually analyze the populations of the NV0 and the NV minus. So we apply this decomposition techniques to study the population of the NV minus and the NV0, and then looked at the this high voltage pulse dependence. So yeah, similarly, we have analyzed that the SIB0 spectrum to measure the change of the population of the SIB. So here is basically the result. So we have that when we have the no pulse, no high voltage pulse, the population of the NV minus and NV0 is almost 50-50%. And then by applying the high voltage pulse, so we decrease the populations of the NV minus, and then increase the population of the NV0. And then for SIB, we increase the population of the SIB minus. Then when we think about the mechanisms, so this is what I thought. So when we apply the high voltage pulse, so originally, since we have the 50-50% populations of the minus and zero, so Fermi energy of the diamond is almost in the middle of this boundaries. So minus and zero is same populations. Then when we apply high voltage pulse, so we inject the electrons from the bottom side of the diamond, and we eject the electron from the top surface, which we are looking at. Then this will effectively lower the density of the electrons on the top surface. So this will lower the Fermi energies. Then by now pulse is gone, and everything is diffused back to original conditions. So principally the dynamics is between minus and zero for NV, and then for SIB, so 2 minus and minus. So okay, so let me go back. So in the case of NV, so since the Fermi energy is shifted down, so we have more population of the NV0. And then for SIB, so since the Fermi energy is shifted down, so we have more population of the NV minus. so that there is a charge state conversion from 2 minus to minus. So then dynamics is basically a two-state dynamics. So by considering those two states and the different rate from the one state to the other state, so we can model the experiment, and then by fitting the data with the models, so we found that we can explain our observations very well. And then more recently, so we developed the systems in my lab to measure those in by using the pulse measurement. So this is a measurement scheme. So in the beginning, we apply high voltage pulse to make the charge state conversions, and then after that we wait, and then we do the measurement. So in this way, we can first of all distinguish the effect between high voltage pulse and the lasers. In the previous experiment, we apply laser and high voltage pulse simultaneously, but by doing this way, we can make sure this is only coming from high voltage pulse. And then also by changing this delay time, we can measure how long we can keep the induced charge states. And through this lifetime measurement, we found that the charge states can stay as long as hundreds of the millisecond, and then to the several second. So which is actually a very long time scale compared with the time scale we use it for coherent or quantum manipulations, which is usually in the nanosecond, microsecond time scale. So yeah, and then also we apply the same method to the nano diamond. So this is micron size diamond powders. And then we found out that we can actually change the charge states of the diamond powder too. So in this case, the diamond has a lot of boron doped. So Fermi energy is lower than the bulk diamond. So bulk diamond was started from about 2.7. So in the case of this nano diamond, it has a much lower Fermi energies. And then by lowering the Fermi energy, now we change the populations of the SIB minus to SIB 0. And in addition, so this diamond powder contains the silicon borons impurities in addition to silicon vacancies. So looks like this high voltage, the method can manipulate those charge states. It's not just on the NV and SIB, but also any kind of actually the defect. So we think that, so since we changed actually the property of the substrate by using the high voltage, so we think we can apply this method to different type of the defect centers. So for instance, group 4 vacancy centers is very interesting because all of them has a narrow emission lines. And also this can be applied to different materials, silicon carbides or hexagonal boron nitrides. So all of them has an interesting defect and they all have a charge states. And in addition, this electrical control is very interesting. And eventually, so we're now interested in make some single photon device based on that, using electrical control, and then also some PN junctions of the diamond. Okay, I think it's about time. So yeah, thank you for listening my talk. So this work is done by actually lots of graduate students, including the Ben Fortman, Laura, and Yuhan. They already graduated, and also exchange student Shunki, and then also the current student Ifan Son, and then Nabiha worked on squeezing project. And then, yeah, also Ifan is working on this NV-centered charge state conversion project. And then also charge state conversion project is a collaboration with Steve Cronin Group at the USC. Thank you for your attention.
Thank you, Susumu. Great talk. There's an echo coming in, yes. let me check. I mean, let me check if there are
Yeah.
questions. It seems there is one question. There is
Okay.
one question from an anonymous attendee, and the anonymous attendee is asking, can this squeezing phenomena also be realized in other non-commuting operators, such as position and momentum, or is it only restricted to spin? If so, why?
Well, of course, this can be applied to any operators which doesn't commute. Yes. It has been demonstrated. Well, so for instance, yeah, so position and the momentums. So these are demonstrated in the LIGO systems. So based on the non-commuting of the position and momentums.
Thank you. Is there any other questions from the audience? Okay. I have a question, and that's with respect to the silicon vacancy or germanium vacancy. So, you can create multiple vacancies inside the diamond, but how do you differentiate these vacancy with the defects that are generated? I mean, when you implant this, or when you're growing the diamond, you create these artificial vacancies. How do you differentiate those vacancies from the defect related non-recombination center vacancies, because they are all photoluminescent?
Oh, so for instance, well, spectrum is well, if the spectrum is different, we can distinguish easily. So for instance, are you talking about the different defect or different charge states?
Different defect states, because there are two things. Yeah, you mentioned that there is defect states as well as the charge states. I mean, so yes.
Yes, that's right. So for instance, okay, so this case is silicon boron and silicon vacancies. So spectrally they are distinguishable. So this silicon boron is corresponding to SiB, SiB minus. And then this SiB silicon vacancy is SiB minus. And then there is a SiB 0, so which is located 950 nanometers. So the spectrally different. So we can distinguish. Yeah.
Okay. So the wavelength is different, or the frequency is different.
Yeah, wavelength is different. That's right. And I'm not sure about the silicon boron zeros, if this actually gives the emissions or not. But I'm pretty sure if emit, then wavelengths will be different.
Okay. Okay, great. Thank you so much. Let's once again thank Professor Takahashi for this wonderful talk. So next week's presentation, we have next week Professor Liang Feng from University of Pennsylvania. He will be talking about topological photonics. Thank you so much for participating in this. Bye.